Okay, good evening, welcome. Let me remind you what we are doing. I know this is a quite an intensive course. We have to look at many things in order to work on this subject, but it's also interesting to see the connection between these different subjects. Oh, by the way, I just put this. Remember, you are free to write or to do any exercise or to work on any examples. I'm going to mention a few more examples which can be worked on today, or I mentioned a few last week. You can choose. If you don't know what to do, ask me, but you need to practice or to do something. So don't forget and don't wait until the end of the semester, please. Last time I recall that there are two main types of random variable. I say main, but there are other ones. Either the absolutely continuous one, so it's when you have a probability space, so somewhere you have a space omega, a set of subset of omega on a measure p, a probability measure, and random variables which are absolutely continuous are functions on omega with value in Rn, and the measure is what we call absolutely continuous, but it means you have a probability density function. I don't recall the details now, but it means you have a function from Rn to 0 infinity, such that the measure of any set is just an integral. Or you have random variables which are from omega to either a countable set, so it means a set which has a cardinality of n natural numbers, or finite set, and then it's not a continuous function, but you have the notion of PMF, probability mass function, which associate a number on each point of this set, and the sum of these values makes 1. Then we discuss when you have two random variables. So when you have two functions on a set omega, and I just thought about one example, because later on we can speak maybe about weather forecast because data assimilation has been developed for this. So for example, you look at the system of Earth or anything, and the two questions are about humidity and temperature. You are asking two questions on your system. You don't know if they are related or not. It will be related to this notion of independence, but these are two questions you ask on your system at any point, instead of just one question. So whenever you have two random variables, you can define just this pair of x1, x2. Now it's a random variable from omega to these two copies of lambda. You can define the joint measure because it's also a random variable. And whenever you have this notion of marginal measures, which is when you integrate or when you consider all possibilities on one of these two sets. And once you have this, I have introduced this notion of cross-covariance matrix. What is more common is this covariance matrix. This is just a special case of this definition. Whenever the set lambda is one that is R, you can define, so when it's univariate, you can define the correlation. You cannot do it in the general case because otherwise you would divide by matrices, which is not allowed. And you have this notion of independence. Then I also speak about a slightly different subject. Whenever you have two marginals, how can you say something about the system which generate these two laws? So it's a kind of converse problem. You have the marginal PDF or PMF, and you want to reconstruct or say something about the underlying system. But of course, you have a lot of freedom. So there are some better solutions than others. So I mentioned this. Then you have also this notion of conditional probability. A certain formula which I have written, which is called the disintegration formula, and a lemma at the end about a link between marginal PMF and conditional probability distribution function. All right. It's a lot of things, but you can find this in the notes. And then I just started to motivate what we are going to do today. So this is 2.2 about discrete time Markov process or Markov chain. sometimes called Markov process, sometimes Markov chain. So what I'm just going to say now is in 3 pages of these notes. So I'm going to be to summarize. So we consider function f from Rn times z to Rn. So I come back to this initial dynamical system, and we consider x, which is a function from the time, and it's discrete time, so from z to Rn, and a dynamical system, the system. This was our initial example. We have x of at time n plus 1 is f of xn, and that's it. N in z. This is a discrete time dynamical system. If there is no dependence on n, so if this is absent, so if there is no explicit dependence, the system is autonomous. I think I didn't write this word. The system is autonomous. And so it means if I give you 1 point for x at time n, you can compute the next position. If x of n star is known, you can compute x of n star plus any k, just by iterating this formula, right? So there is no problem. But as we have already discussed at the very beginning, sometimes we don't know precisely x n star. So it's better to think about a subset, that x n star is in a subset. So more generally, we consider a subset, and I'm going to keep at time n star. So this is a subset in Rn. And consider that xn star belong to this. Instead of just considering 1 point, I'm going to consider 1 set. And now we can iterate these, or this set. So then we can consider A of n star plus 1. This is going to be f of A n star and n star. And what is this? You can guess the definition. It's a set of points f of x n star with any x inside A of n star. If we do a picture of what we are just doing, before I had just 1 point, and I was computing x at n star plus 1, and so on. Now, what we are going to do is to consider a certain set, A of n star, saying that x n star is inside, and then this is A of n star plus 1, which is quite natural definition. But what is the next step? Is now to speak about probability. To say that there is a certain probability that at time n star, I will forget the n star in a second. At a certain time, there is certain probability that the system is in this, And then we would have the same probability that it is in this set. So now we are going to mix this notion with the notion of probability. Now, associate probabilities. This. I'm just trying to motivate the final definition that I'm going to introduce. So what is it? What I mean by this, consider a, let's say in Rn, maybe it's a Borel set, but let me just be not too precise. So I consider A in this and define, it's not very precise. Let's say a bold P, but it's not exactly the P of the probability space. It's just a bold P, N of A. It's not a precise definition. This is a probability that the system is in A at time t. Or at time n, sorry, at time n. So for given A, I define a certain number, which is a probability that my system is inside this A at time n. And then maybe there is a mistake in my notes. Then you can wonder, changes if the probability that f of A n is equal to this P at n plus 1. And you can wonder if probability that your system is in this set at time n is equal to, now you let it evolve, the probability that it is in this set at the next time. This is a natural question. And, or you can look, or you can also compute what is the same probability at n plus 1 that it is in A. So these are natural questions. What is now, I keep A fixed, and I'm asking what is the probability that at time n it is in this set, or what is the probability that at n plus 1 it is in this set. So these are natural questions that you have when you have a dynamical system and some set A in Rn. So with this, we want to introduce some random variables because, yes, there is a question. Again, it's not completely rigorous now, but I'm trying to motivate. So we would like to introduce random variables xn from a certain space to Rn so that this Pn at A, now I want to write it more precisely. This is a, if I write omega, it means that I have a probability space. So this Pn at A would be the probability that Xn is inside A. And this has a precise meaning that we have introduced. Be careful, it's not it's an index. It's not something power n, it's just an index, but I don't want to use index here because if it is a vector, it would be confusing. So I keep this notation with the upper index or exponent. And this can also be written as the expectation of this. Probably I have not introduced this notation, but what is this function chi A at X? It's a function on Rn, and it is 1 if X belongs to A, and it's 0 if X does not belong to A. This is called the characteristic function. And in fact, these two things are just the same. And if this random variable is absolutely continuous, this is going to be an integral on A of pi xn of x. If, let's say, if xn absolutely continuous. This is what we would like to do. Introduce some random variables, and then which are related to our system, and have a way to speak about the random variable taking values in A and define its probability, and it would be the probability that our system is in A at time n. And of course, if we do this for all n, we would like to understand the relation between xn and xn plus 1. So this is a natural question. And so if we can define such a random variable, then what is the relation between xn and xn plus 1. Okay, so this can be done, and we are going to deal with this, but we are going to do it even in a slightly more general framework. Because so far, the system is what we call deterministic. I had a function f, and with this function f, I can just compute the iteration. But so far, the evolution was deterministic. And what I mean by this, it's given by a fixed but we will consider x at time n plus 1 is this function of xn n but plus something which is a psi n. What is this psi n? It's going to be one new random variable. Psi n and down. No. Oh, no, it's not the n component. You're right. So probably I should have also put upper index. No, Okay, I just follow my notes for now. No, it's not the component. This, and you should guess it because this is n-dimensional. This is n-dimensional, so this has to be capital N-dimensional. Right? So this is a certain random variable with maybe a given law, with a certain law. And this is no more deterministic if we have a random variable at this point here. So we would like to have a framework which contains everything like this. And the framework is precisely, so the correct framework is precisely, or the framework consists Markov process. I'm going to give now the definition. And let me say this is in discrete time because the n is discrete. If you want to have in continuous time, it also exists. Markov processes in continuous time also exist, but the theory is more complicated. I'm dreaming about doing one course on this, but it would be quite advanced and probably difficult. What you can do, I'm not going to do it, but let me just make a comment. You know, I'm considering n integers. But what you can do is you can take smaller and smaller intervals. So instead of considering n belonging to n or z, we can also consider, you don't have to write this, n times a small delta t, whatever it means, a small interval. And then, so it means instead of considering big interval like this, regular, we can also consider much smaller one. And you can also do a limiting process. So take this delta t going to 0 in a suitable sense. And then if you do it properly, you get Markov process in continuous time. But this is not easy, and it's certainly not the best way to introduce Markov process in continuous time. But yeah, sometimes you find that the interval between two events is n times a certain constant, which is small. It's simply that instead of considering integers, we consider things which are smaller. This is just for information. But going from n to this is not a big deal. Then what is more difficult is to take a limiting process when this delta t goes to 0. Okay, so just since I'm here, just let me emphasize that n, I'm going to consider this set. I'm changing every week, but now it contains 0. So what is first a stochastic process? So the first definition, now it's slightly more precise. A discrete time stochastic process this is not difficult, is a family of, it's a family xn, n inside n, of random variables. On what is important is that they are all defined on the same probability space. So they're all defined on this. I'm taking values in a measurable space like this. For example, Rn, or a discrete set. What is important in this definition? This is very general. It's just a family of random variables, but they're all defined on the same probability space and they all take the same image. It doesn't mean that they are all the same. It doesn't mean that they are all identically distributed. No, it simply means they are defined on the same space with the same image. But this is too general. I mean, this is the broadest definition. You cannot do anything. So now the second definition, which is more restrictive, discrete time Markov process. And this is not the most general situation. Values n. So I'm going to consider this set, this measurable space as Rn for now. The discrete time Markov process is a stochastic process. So it's a family of random variables like this. The stochastic process defined. It's a stochastic process is each xn absolutely continuous maybe I should say each xn, maybe I should just write from omega to Rn, because I have mentioned absolute continuity only when it's with value in Rn. So with each xn from omega to Rn, absolutely continuous and satisfying. This is the main condition now. Satisfying n in n bigger or equal to 1 xn I will explain. Okay, what is the meaning? So each random variable, if it is absolutely continuous, remember, it has a PDF, probability distribution function. So this is a PDF, probability density function of xn. Because if it is absolutely continuous, we know that it has a PDF. So I indicated by pi index xn. Now, it's a conditional probability. And last week, I have introduced conditional probabilities. And so it's a function of one variable, but conditioned by the knowledge of many other things. So last week, I did it for 2. I introduced px1 of x1, x2. This is what I have introduced. But this x2 can be a vector. So in fact, this notation contains this one. And the thing is, so xn knowing all the previous values is the same as just knowing the previous one. Not, you don't care about all the other values. So what is the meaning of this? It means that if one knows xn minus 1, the other xn minus 2 up to x0 do not provide any additional information. This is the meaning of this. And of course, this is an assumption. But it turned out that this condition is satisfied by many, many systems. And this is why this definition is interesting. I'm not claiming that everything is described by Markov chain or Markov process, but many systems have this property that if you know your system at time n-1, you don't really care about what happens before. This is this definition. So Markov chain or Markov process is a family of random variables. I assume here that they are absolutely continuous and that their density satisfies this. Right? And probably later on, I will just write this pi n instead of pi xn. So don't be surprised. Now, this formula has different consequences or different equivalent formulations. So let me write it as a remark or several remarks. Last time I also mentioned the disintegration formula, which was valid for all random variables. And it was precisely in terms of conditional probability. Now, if we assume this, it simplifies this disintegration formula. So this equation is stated the disintegration formula. And now it takes the following form. It was pi of xn up to x0. Be careful. I put them in this order, as I already mentioned last week. You can choose the order you just present them, as long as you are coherent with the variables. But for today, I present them in this order. So this xn up to x0. So what is it? This is a joint probability distribution of these n+1 random variables. So this is instead of 2, I consider n. And the disintegration formula was a certain formula for this. It was pi of xn at xn, knowing xn minus 1 up to x0. But now, because it doesn't matter knowing further in the past, I can just write this one times pi xn minus 1 at xn minus 1, knowing xn minus 2 up to pi x1 knowing x0 times pi x0 of x0. Right? So it's a simplification of the formula which I have written last week, because last week I had xn minus 1, xn minus 2 up to x0. Here we had xn minus 2, xn minus 3 up to x0 and so on. But because of this Markov property, I can just simplify this formula. All right? So this is in fact an equivalent version of the Markov condition. If the disintegration formula takes this form, then it implies also this. And a third equivalent version, this is, let's say, the remark one. Another one is star implies what is called the Chapman-Kolmogorov equation, which says this: the probability density function of xn. So I really take care of always writing xn for a random variable, and then xn is a point. This is a point in Rn, if I follow that we are in the system with values in Rn. So this is equal to integral over Rn of the conditional probability xn, knowing xn minus 1 dxn minus 1. It means the probability, or when you evaluate this function at xn, it is this integration over the distribution of xn minus 1. I mean, as you can observe, I could, but it's not really not really a simplification. I could just call this x on x. This power n minus 1 has not really any meaning, because you remember it's a variable of integration, so it doesn't mean so much. But because we are dealing with many variables, it's always easier just to keep track of which one it is. But you can replace, if you don't like it, you can replace xn minus 1 by just x everywhere. You get the same equation. But later on, when you have many integrations, it will be misleading. This is why I keep writing xn minus 1. So this is also a formulation of this Markov process, that knowing, I mean, if you know this conditional probability and integrate over all possibilities at xn minus 1, then you get this value. And if you want to write it in a shorter way, so I'm going just to write this equation in a shorter way. What we have, if we look carefully, we have a function is equal to a certain action on this function. So it can be written, this function, a certain what is called an operator p x n minus 1. Or simply, I'm also going to write simply pi n is p minus 1. This is just a shorter notation. And what is this p? In this case, p, the operator. It's the first time I use this word, the operator acting on function. I on a function, oh no, p on a function f evaluated at n, it's this integral. I'm just writing or introducing a shorter notation. And this is, if you check, I'm just copying what is on the left. And instead of giving this complicated name, I'm just, dx. is a dx. I'm just using a simplified expression. So what I'm just saying is this relation can be written in a shorter way like this. But what is this P? It takes a function. It takes this function. This is a function. And it sends it to a new function. This is called an operator. So this, yeah, if you remember the very first definition of a function, it takes an object and it sends it to another object. This P take a function and send it to a new function. That's it. And how it does it, it takes an integral of a function of two variables and it integrates this function f and dx. Any question or remark? I hope it's clear. Now, this is in the continuous setting. Let me just mention the discrete setting. What is discrete here? Or what is continuous here? It's the fact that we have with value in Rn. But sometimes or quite often, we also have random process with values in a discrete set. So remark. If this set lambda is finite or countable, finite is always the simplest one. Is finite, namely, the set lambda 1 or lambda 1, lambda 2, either up to infinity or a finite set. We say that this family of random variables is now this random variable from omega to a discrete set is a discrete time. Discrete value. Or sometimes it's also called discrete state space. But I prefer discrete valued. Maybe I will change discrete valued Markov process. Now what is the analog of the Markov property, the main property I mentioned, but in the discrete case? So it's a discrete time and discrete valued Markov process if the probability, but remember for discrete valued, I have the PMF, probability mass function. So it associates a number to points. So probability that X takes the value lambda J, knowing Xn, knowing Xn minus 1 is equal to lambda K up to X0 is a lambda I. I'm just saying the probability that this random variable takes a certain value in this set, knowing that Xn minus 1 is lambda K, blah, 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 up to lambda 0 is still another one. This is equal to P of Xn is lambda J, knowing only the previous one. And this is usually denoted by PJK. But if I want to be what do you observe? There is a mistake on this, on what I have written. What is a mistake that you shouldn't do? When you have an equality, you should have the same number of information on the left and on the right. Do you have the same information on the left and on the right? What is missing? No. I mean, what is missing here is there is an n. So I should also indicate somewhere, if I give a notation, if I introduce the probability that xn is lambda j, knowing that xn minus 1 is lambda k, the information about lambda j and lambda k is encoded here. But what is missing is time. So I should, in fact, write n here. But why most of the time we don't write it? Because if we assume that our system is autonomous, then this probability is often independent of time. So let me mention it. We should write it. So we should keep track of n. N. So in this notation, I should have an n. If the system, of course, there is not really any system here. I'm just describing the general theory. But if the system is non-autonomous, but most of the time it is autonomous, but you can forget n. If the system is autonomous. Just be careful about this. But yeah, whenever you have an equality, the same information should be visible on both sides. Okay, so this is the natural notion of Markov. What you know before xn minus 1 is not important. Now, these p, j, k have a certain property. What can you say about the sum of p, j, k? What is it? I think I hear somebody's. It should be 1, because it means the probability that your system from the state k goes to any values, any lambda 1 up to maybe a lambda infinity, it has to be 1. And again, if you have a dependence on n, I should mention it. And in this setting, Chapman-Kolmogorov equation so I'm just translating what was written for PDF. I'm translating it to PMF. The probability that xn takes a value lambda j is given by a sum of p, j, k. The probability that and I sum over k. So this is the same equation as before, but now in terms of discrete valued. Before it was continuous valued. By the way, this family PJK has a name. This PJK is called, either it is a transition, it's called a transition matrix. And it is indeed a matrix if lambda contains only a finite number of values. If this set lambda, which was lambda 1 up to a certain lambda n, if it is finite like this, it's a matrix. It's an n by n matrix. Now, if it goes up to infinity, you cannot really speak about a matrix. So it's called the transition operator. So it's a transition matrix if this set is finite in the transition operator. If this lambda is just countable, but not finite. This is just a name. And now if I want to make this again in a shorter version, we can write, because I want to have the same equation. Pi n is equal to this p pi n minus 1, which is exactly what I have written before. And what is it? This pi n. Now think about it. Take the finite dimensional case. This is a vector. This is a matrix. This is a vector. So what is pi n? Pi n. It's a vector. The first entry is the probability that xn is equal to lambda 1, probability that xn is equal to lambda 2, and you continue. If it is finite, it's just a vector. If it is infinite, it's a rather huge vector. But the point with this notation is it was the same before, except that the interpretation is slightly different. Before it was a density function, a PMF. Now it is this vector. No, PDF, sorry, it was a PDF. Now it is this vector. Okay. Is there any question or remark? So we have seen this Markov property, which is quite natural and appears in many contexts. And this is a framework. And in a few minutes, I'm going to show that the original example I have presented fits into this framework. But let me introduce one or two more definitions. The next one is important if you study what is called dynamical systems. I'm not sure that for data assimilation it's so useful. I will explain why. But still, you can. It's good to know it. The solution equation I is called a solution. I should give a name. A solution pi star is called a steady state. So here, what is the meaning of this? You can either take it in the continuous case or in the discrete case. This is an equation. A vector is equal to a matrix applied to this vector, or it's a density, it's a function, is this operator acting on the same function. It's like an eigenvalue, eigenvector problem, except that it's really an eigenvector, eigenvalue problem. If we are in the finite dimensional case, if we are already in the infinite dimensional case, with a countable set, or if we are dealing with functions, it's slightly more complicated, but still we can look for a solution of this equation if it exists. If it exists, it's called a steady state. And why is it important? Because it means if your system is described by this, it doesn't evolve anymore. It doesn't mean it stays exactly at the same position. Maybe there is a cycle or anything, but it means on average, it stays at the same, in the same structure. So why is it? So this is important for dynamical systems because you are looking for solutions which do not evolve anymore. However, for data assimilation, since you insert new data always, every time, I'm not sure that this is really an important concept. But nevertheless, it's good to know that the solution of such equation is called a steady state. And the corresponding measure I will explain. Or it's a good case. It's called invariant. I mean, this is still in the definition. These are just two words. So if you have a solution of this, remember, this is a density. So it's a function which, when you integrate it, gives you 1. So we associate what we just call the measure. Instead of just considering the function, we prefer to write it like this, but it has not really so much meaning, so don't worry. This is just one way to associate. This is a measure, so it associates to any set in Rn a certain number. But because it's stable, we call it an invariant measure. Or this vector, which, if you think about it, it's the sum, again, is 1, because probability that xn take any value is 1. So this is also called an invariant measure. But as I said, this is important for dynamical system. Maybe you will see this for data assimilation, I'm not sure. But the good point, if I0 is this pi star, pi0, remember, is the same as pi at time x0, so pi for time 0.
What's x0 is it now?
You decide if the 0 time is now or tomorrow or yesterday or 3 billion years ago. I mean, I have introduced pi n for n starting at 0. I mean, n in n. This is just the first one. Now, when is the first one? You decide. But if this probability density function for n is equal to 0 is a steady state, what does it imply? It implies that x, or it implies that pi of xn is the same steady state. It's no more on the blackboard, but remember before we had a xn minus 1. But precisely if you start at 0, which has a property that it just keeps the same shape, you can iterate this and get that this PDF is the same as this one. And the second fact is that the expectation of any function of xn can be computed at x0. So this is a boring situation. Nothing is changing. And this is E of F of, okay, I have not introduced X star, but you can guess what it is. If we have a, no, maybe I should not write the last one. But it means any expectation, the expectation of any function at xn is the same as if you compute it at time 0. But of course, this is a very special situation. I'm not even saying that it always is this. It depends on your system. All right. There is one more notion I want to introduce, and then I will check that we are reading this framework. I want to introduce this because once I face it and I didn't know how to understand it, so I prefer to give it to you. First, the discrete time. Out of process. Is weakly stationary. By the way, when I don't specify if it is with value in Rn and absolutely continuous and with value in a discrete set, it means that we can do both. I have introduced both, and I have introduced this notation, which is valid for the two settings, even if the interpretation is slightly different. So we say that it's weakly stationary if for all n1, n2, and n belonging to n, what we have. The expectation of so the expectation of this random variable xn1 or xn2 are the same. So the mean value is not changing. And think about like a conservation of energy. The energy is conserved for all time. And the covariance of xn1 plus n, xn2 plus n is equal to cov. I have introduced this covariance. It was called cross covariance matrix because I'm considering two different vectors. It is a covariance matrix if I consider the same vector. If I consider two different vectors or two different random variables, it's called the cross covariance matrix. And this condition is that if you compute it for n1 plus a certain n and n2 plus a certain n, you can just simplify these two n and you get the same. So it's a kind of invariance in time. If you measure something between two times, or two things between two times, but with the same interval between these two times, you get the same thing. This is called weakly stationary. And again, there are many systems which respect this. But why I introduce this is for the next, why I introduce this is for the notion of autocorrelation or autocovariance. Once I didn't know. So for weakly stationary Markov process, we define autocorrelation or apparently it's the same, or autocovariance. Autocorrelation or autocovariance function. Oh, it's a matrix. But the matrix is a function. Oh, no, okay. No, it's correct. I will explain. It's a autocorrelation or autocovariance function C NM, which is cov of xn xm. So indeed, this is a function. It's a function of 2 times n and m, and it is this cov of xn xm. Now you observe that if precisely it is weakly stationary, so if we have this property mentioned there, I can write it as C of 0 m minus n if m is bigger than n. If I did not specify in which order, so you just take the biggest one and you call it m, the smallest one you call it n. So in fact, it's only a function of the difference because of this property. And this is called the autocovariance or autocorrelation. And what does it measure in a sense? This function. So it's a function. It's a function of 2 indices, but in fact, it depends only on the difference. So this function. Now, what kind of values it takes? It's a function of 2 integers, but it takes values in matrices. Last week I mentioned this is n times it. In this case, it would be n by n. It cannot even be of a known square. But in this case, these 2 vectors are of the same size. So for any n and m, this is a matrix. But it's a function because it's a function from 2 copies of n with values in the set of n by n matrices. This function with values in n times n provides, this is not very precise, but it provides an information about the loss of memory. The Markov chain. Or Markov process. So the parentheses here. Of course, like this, it's not so meaningful, but if this covariance goes to 0, it means that when the difference is becoming bigger and bigger, the system does not remember its position or its state before. Okay, so what is, I should do a picture. If capital N is 1, this function has usually this shape. So let me write Let me just do it. Usually, for n is equal to 1, C 0 n m minus n is, this is a typical picture. And this is m minus n. You see, and the faster it decay, the quicker the memory loss is. But of course, this is not very precise. But probably you would see, or yeah, this is a notion which appears quite often, autocorrelation function, and you have to understand what is the meaning. If, by the way, if the system is not weakly stationary, you can still define this, but you cannot simplify, so you need to stop at this definition. And then it's, when you represent it, it's a function of two variables, so it's more complicated. Still, it is possible. So you can define this even in the non-weakly stationary case, but simply the representation or the interpretation is slightly more complicated. All right. Any question or remark? There's only one person online. I hope you have no question, otherwise you can ask. Now, we have to check that the initial system I introduced is a Markov, or defines a Markov process. Otherwise, I'm speaking about nothing. So let's check that at least our initial example, which is already quite general, fits into this framework. And we are going to learn the computation also. So let's check. The initial example. It's this framework. So what was the initial example? I'm going to consider an autonomous one. So we consider f from Rn to Rn. I'm going to consider family psi n in a sequence I, D. I haven't introduced, so it's a good time to do it. ID absolutely continuous. Random variables. Are you sure you have an important question?
No.
Okay, what is your question?
Random variable taking value in Rn.
Yes. You are right. So I have to explain what is it. But again, your question will be answered in the next slide, but because of the problem of dimensions. What is IID? This means independent and identically distributed. And what means identical? Independent, we know what it is. What means identically distributed? It means they follow the same law. All of them follow the same law, which I define like this. So they all have the same law. This is why I don't specify G. So a sequence of absolute continuous random variable. And let 0 at time 0 Yeah, and absolutely continuous. And the variables we assume. Or we define, we set xn plus 1 is f at xn plus psi n. This is what I call the initial example. So now it answers your question. If f is from Rn to Rn, it means everything. So this has value, these values Rn. So this, remember, random variable is a function on this probability space with value in something, and here this something is Rn, and it means that also this psi n is also a random variable with value in Rn, otherwise you have a problem of dimension.
Practically for every n, the random, if I take the noise, like the unknown random variable kind of changes.
Yes, so this is indeed often called the noise. Where is the red? This is often called noise. So if I do the picture I did before, it's not really precise, but remember An, I want to compute the image of this. Don't take it very seriously, but I should have here f of An. This is a deterministic part, but I have some random noise. So it means this is not exactly this, but it is something more like this. This would be f of A of n plus psi n. So it means instead of having a deterministic image, there is some noise everywhere. So your system, there is a deterministic part, but there is an unknown part or not precise part that you modelize by some noise. This is the idea of such a model. Now, I need to check. I want to do two computations. The first observation is that it is indeed a Markov process. So one has, what is pi xn of xn knowing xn minus 1 n minus 1 up to x0. And if you use this formula, xn is given by this. So it means this is f of xn minus 1 plus psi n knowing xn minus 1 to x0. It is, yes, it is psi n minus 1, right? And now this is clear. In this formula, because the psi n are all independent of the points, oh no, sorry, not the last one. You keep it, the last one is important. Xn minus 1. But you can forget everything else because your next point is given by a function of xn minus 1 plus something which is completely independent of the other things. So this is a Markov property. It means this is pi xn of xn knowing xn minus 1. You don't need the other things. So this is a Markov property. But we can say more than this. Okay, when your computation was very useful. Now I know how to do it. So let's do one more computation. For a fixed and what we have. Observe that xn plus 1 is equal to f of xn plus psi n. So it means if I know a precisely xn, then the relation between x plus 1 or x plus 1 is given by this. So what does it mean? This is just a number, or this is a vector, more precise. This is an element of Rn. Now this is a function, and this is a function. But these two functions are just related by a shift. I mean, this is a function, it's equal to this function plus a vector. So it means if this function has if it looks like this one, if this is, or let me write now, pi of n plus 1, you have somewhere else the same function, pi of psi n, and there is just a shift. So you have the vector f of x n, which just shift this function to another place, right? This is just a given vector. So what does it imply? I will take 3 more minutes, but I want to do it because it's our first real computation. So it implies if I compute pi xn of n plus 1, n plus 1, n plus 1, knowing xn, this is a conditional probability, which is, it is the distribution, yeah, it is this distribution, in fact. I should write knowing xn, because as I said, xn is given, and here I should put a given xn, not a random variable, the small xn. So this distribution, I'm claiming that this is pi psi of xn minus 1 minus. This is an exercise, shows this. This is a one-line exercise, or maybe 2 lines. You just have to remember what is the relation between random variable and the distribution. So, try to do it. If you understand this, if you can prove this, and I said it's a 1 line or 2 lines, but you need to really think about what are these objects. So the function, this is a function evaluated at 1 point, but knowing xn is the same function shifted like this. But you have to understand why it's a minus here. So this is an exercise. But from this, so this I let you do it. It means that the probability that xn plus 1 is inside A, which I can write as integral on A of, no, this is not correct. Knowing xn. Probability that xn plus 1 is a certain set, knowing xn is by definition the integral of A of phi xn plus 1 of xn plus 1 knowing xn. This is the definition of this density. This is the rho of this density. Now, by the previous equality, this is the integral on A pi xi of xn plus 1 minus f of xn. Yes, I shifted, you're right. Oh no, simply I couldn't read properly my notes. It's a plus, you're right, thank you. Yeah, thank you, it's a +1. Yeah. Now, I'm using star here. And sorry, I forgot the D. I'm integrating over dx xn plus 1. Or I can call it just x here, it doesn't really matter. But okay, let's keep the xn plus 1. Okay, let's keep this and let's do one more computation and I will use this. I will compare. Because here, look, this is a conditional distribution. It's knowing xn, but if I don't know it, so now the probability that xn plus 1 is in A without knowing xn minus 1. But by the formula Chapman-Kolmogorov, this is the integral on A of pi xn plus 1. This is the definition again, but now Chapman-Kolmogorov, it's integral on A of integral on R of n plus 1 of x. And I have two integrals. This is Chapman. This, or it's also simply the Markov property. This guy is equal to this one integrated with the density of xn. And now, what is the next step? Now I replace, again, this guy appears. So I can replace it by the right-hand side. I just need to be careful about the name of the variables. Pi psi of course, I changed my notations. N plus 1 minus f of xn. I hope there is no mistake. Pi xn. And the first integral is dxn, and then dxn plus 1. Please check that I have not done a mistake when I did the replacement. And now if I compare this with this second equality, so what we have an integral over A of something. So pi, I hope there is no mistake. So let me just check. Let me simplify the notation just to fit with my notes. This is not necessary, but you can keep it. And so xn minus 1 or x plus 1, we can just, and yes, let me keep the other one like this. This is correct. So it fits with my notation. So now I compare these two things because so let me write, I don't see the point now. I just write it. It means that pi of xn plus 1 at x can be written as this integral on Rn there is a Rn. Is it your point? So let me just finish. I'm a little bit lost, I confess. Rn of Q1, do you see a mistake? Ah, thank you. So I simplify. It's just xn plus 1. Okay. Xn, yes. But again, you can just call it. So, oh yeah, this corresponds. Because this from, maybe I put the one at the wrong place, sorry. One is not this, probably. If I want to compare, I think so. Yeah, sorry. Now I compare 1 and 2. And what we observe, we now, okay. This is and is it what I have written? I just changed the name of the, so yes, it's the same. So it means we are in this setting that pi xn plus 1 is a p of pi xn. And you have even a formula for p with p on any function. So let me call this function. I just keep pi without any index, p pi evaluated at x, or evaluated at which letter is x. This integral on Rn, this pi xi at x minus f of all right, this is what I wanted to get. So with this model, we even have an expression for the transition operator. The transition operator acting on any function is by this expression, which is take the distribution of the noise at x minus the function, this deterministic function of one variable, integrate with this function pi of the dz. So we have an exact, of course, it's, if this noise is complicated, it doesn't mean we can solve all the problems, but we have an explicit formula for this transition operator. This is what I wanted to get. So this is the end. In this example, I just recalled, we have checked that it is a Markov process, and we have even been able to compute the transition operator. And this operator P is called an integral operator because clearly it contains an integral. Okay. Yes, so this was the point. I think probably this part was not really necessary. But what is written there is correct. This is by definition. Then I use this Chapman-Kolmogorov equation, and I just then identify this expression with this one, and I get what is here. Now, this part I'm not sure. Okay, sorry for the 5 minutes, or even 7 minutes. Is there any question or remark? So that's all for the general theory of Markov process. Then I had a request to speak a little bit about Bayesian things because Bayes is going to play a role. So I will spend a few minutes or half of the next lecture about Bayes theorem and its consequences. And then probably I will start with the Kalman filter. And by the way, yeah, in the notes I also mentioned, but probably just after this, a few exercises or a few examples, but yeah, it's exactly in the next part. So if you have some time, please look at what I mentioned, the few exercises I mentioned last week, or try to really understand what is going on. It's important to play a little bit with these definitions. Okay, thank you.